Welcome back. The last topic in this learning objective is to know some special sums that will appear regularly. Let's start off with a question. What happens if you sum the natural numbers from 0 up until n? That looks like 0 plus 1 plus 2 plus ... plus n. Writing that in sigma notation looks like this. The sum as k goes from 0 up to n of k, that sum has a nice formula. It's n times n plus 1 over 2. It's a formula that you need to memorize, and we'll talk about how to remember this formula shortly. As an example, what is 0 plus 1 plus ... plus 100? In this case, we're starting from 0, going up to 100, and so we can apply our formula 100 times 101 over 2, which is 50 times 101, which is 5050. So how can you memorize this formula? What are we doing? We're adding 1 plus 2 plus 3 plus 4 plus ... up until n. If we take that triangle of dots and we flip it and we put it right next to it, we've made a rectangle. There are n rows in this rectangle and there are n plus 1 columns in this rectangle. So 2 times the sum is equal to n times n plus 1. Solving for Tn gives us our formula. These numbers are often called the triangular numbers because of this triangular shape. And they start off 0, 1, 3, 6, 10, 15, etc. You may have noticed that n times n plus 1 over 2 is the same as n plus 1 choose 2. This leads us to a quick tangent. What happens if you add up the triangular numbers? What if you take the sum from k equals 0 up to n of k choose 2? That looks like 0 plus 1 plus 3 plus 6 plus ... plus n choose 2. And when you sum those up, that gives n plus 1 choose 3. Those numbers start 0, 0, 1, 4, 10, 20, 35, and they're often called the tetrahedral numbers because you're building them by adding triangular numbers together. When you layer them in 3 dimensions, you end up creating a tetrahedron. The proof of this fact comes directly from Pascal's triangle, and it's part of a family of a similar type of identities. Now let's go on to a couple more sums that you should know. What happens if you sum positive odd numbers together? That is, if we take 1 plus 3 plus 5 plus 7, and you keep going up till some odd number. To represent that in sigma notation, we take the sum of 2k plus 1 as k goes from 0 up until n. The surprising answer is that that sum is always equal to a square number. The sum from 1 up until 2n plus 1 is equal to n plus 1 squared. So for example, if we had 1, 3 up until 19, that corresponds to k equals 0 up until when 19 is equal to 2k plus 1, that is k is equal to 9. And so this formula tells us that the answer is 9 plus 1 squared, which is 100. So why should we expect that the answer is always equal to a square number? Here's another proof without words. If we take 1 plus 3 plus 5 plus 7, you see that at each step when we add an odd number, we're forming a square. So if we start off when k is equal to 0 here, and we go up to k is equal to n in the last column, we have n plus 1 columns and n plus 1 rows for a total of n plus 1 squared dots. And so the sequence S sub n is the sequence of square numbers 1, 4, 9, 16, 25, etc. So a natural question would be, what happens if you sum the square numbers? If we take the sum from k equals 0 up to n of k squared, so 0 plus 1 plus 4 plus 9 plus 16 all the way up to n squared, the sum of that is n times n plus 1 times 2n plus 1 over 6. That's not nearly as nice of a formula as we had on the previous page. As an example, what is 1 plus 4 plus 9 all the way up to 100? In this case, n is equal to 10. We get 10 times 11 times 21 divided by 6, which is 385. Let's also talk about some special products. What happens if we take the product from k goes from 1 up to n of c? Well, that's c times c times c n times, which is c to the n. What happens if we take the product from k goes from 1 up to n of k? That's 1 times 2 times 3 all the way up to n, which is n factorial. And what happens if our product instead goes from m up to n? That's m times m plus 1 times m plus 2 all the way up to n. We can simplify that by multiplying our expression by 1 times 2 times 3 up to m minus 1 in the numerator and the denominator. And if we do that, the numerator is n factorial and the denominator is m minus 1 factorial. So you may be looking at these indices and noticing on this page we started with k is equal to 1, and on the previous page k was equal to 0. Does that really matter? In general, yes, it definitely does matter. Remember, the bounds on these sums and on these products tell us which terms of the underlying sequence we're summing or multiplying. If our sum goes from 0 up to n, then we're saying we are summing a0 plus a1 plus a2 all the way up to an. Whereas if our sum is from k equals 1 up to n, the sum starts at a1 up to an. And so these two sums differ by a0. So if a0 is equal to 0, these two sums are exactly the same. So writing the sum from k equals 0 up to n of k is the same as writing the sum from k equals 1 up to n of k, because when k equals 0, the summand k is equal to 0. On the other hand, if we have the sum of the odd numbers, the first number when k equals 0 is 1, and so these sums are not the same. What about for these products? If we look at the product, where k goes from 0 up to n, we're taking a0 times a1 times a2 all the way up to an. And if we take the product of k goes from 1 up to n of a sub k, our product starts at a1 and goes up to an. So these two products now differ by a factor of a0. So if a0 is equal to 0, the first product is 0. This might make a big difference. The product of the numbers from 0 up to n of k is 0, whereas the product of the numbers from 1 up to n of k is n factorial. It's also nicer to keep track of n factors instead of n plus 1 factors. So often products will start with k equals 1 instead of k equals 0. This all means it's important to keep track of both the lower bound and the upper bound of your index. Okay, that's it for now. See you next time.